On the CLI, we're going to talk a little bit about the background of the protocol, what are the operations behind the scenes, see some of the similarities to OSPF, and then ultimately look at the functionality on the command line interface. Now, as I mentioned, the protocol is called intermediate system to intermediate system, or typically IS to IS, or just ISIS for short. What this essentially means is it's router to router communication, where originally this protocol came from the ISO CLNS stack, where we had two types of devices in the network, the end station or ES and the router in the network, the IS, where there was a protocol that ran between the router to host, which was the IS to ES, and the router to router communication or IS to IS was with the effective routing protocol. Now, where ISIS is typically used is in the service provider core. The main reason for this is that it's scalable for very flat networks. It's a very simple design, it's a very simple implementation, and it supports both IP version 4 and IP version 6 routing. So a little bit later, when we look at the details of features of ISIS, we'll see there's definitely not as much functionality as there is in OSPF, because OSPF is typically designed for enterprise environments, where ISIS is typically just going to be a flat level 2 service provider core. Now, as I mentioned as well, ISIS originally came from the ISO CLNS stack, which means it is not an IP protocol. We'll see that there are some considerations that we have to take into account for this in terms of transport for the protocol, that not all situations will support running IS to IS routing because it is not encapsulated inside of IP, it is encapsulated inside the connectionless network stack or the CLNS protocol. Now, when we enable the process, one of the first things that we need to define with ISIS is what is called the network entity title, or the NET address. Now, the NET address, you can think of this just like how a router ID works in OSPF. It's the value that we use to define the node identifier in the shortest path tree, and that's eventually how we run SPF and do the calculation between the different nodes. Now, the specific format, though, is what typically trips people up, because it's a 20-byte ISO NSAP address, and the format looks something like this, where we have 3 fields in the format. We have the area, the system ID, and the end selector. At a minimum, the address needs to be 8 bytes long, so it means the minimum address length is going to be there. And the maximum is the entire 20-byte address. But the key here is that anything that is beyond the system ID to the left of this is going to be the area identifier. Now, another thing here that confuses people is when we're comparing ISIS to OSPF. OSPF uses areas to enforce its hierarchy in terms of where can we advertise routes within the shortest path tree, and where do we have to advertise routes between SPF domains, like between areas or between ABRs. In the case of ISIS, the area does not map to the flooding domain, or more specifically, it does not map to where you have your shortest path tree defined to other devices that are in what we call the level. So we'll see that the area does have an impact on who we can form an adjacency with, but the area does not directly define the flooding domain. Now, within the flooding domain, or within the area, we also have the system ID. This is like the router ID within the area, so this needs to be locally unique to the area, but for the overall system, the system IDs can overlap as long as the devices are in different areas. Because between areas, we're using the entire NSAP address as the node identifier. Within the area, we're using just the system ID as part of the SPF calculation. And then the last field, the NSAP, or the end selector, that value is always 0. So this means that when you configure the process, you need to at least specify a 1-byte area, and the 1-byte end selector, which is always 0, and the 1, 2, 3, 4, 5, 6-byte system ID. The other restriction is that the area, or excuse me, not the area address, the net address has to be an even number of bytes. So the area address can either be 8 bytes or 10 bytes or 12, 14, 16, 18, or 20, but likewise it cannot be 19, 18, 17, etc. And you'll see that in most iOS versions, if you try to configure it as an odd number of bytes, it gives you an error message. In some versions, it allows it to accept this, but it won't actually work properly. So you need to make sure that it is an even number of bytes. Now, once we define the network entity title, then we need to specify what is the level of adjacency that we want to form with the other intermediate systems or the other routers. And specifically, there are two levels of adjacency, level 1 and level 2, which we typically call just L2 or L1 type adjacencies. Now, the L2 process is what we think of like area 0 in OSPF. So this is the backbone flooding domain. When we want to do inter-level routing, like we do inter-area routing in OSPF, it means that we're going to have a level 1, level 2 router that is summarizing the link state packets as they move from level 1 into level 2. So just like in OSPF, where in OSPF the area defines the flooding domain, in the case of ISIS, the level defines the flooding domain. Now, just like in area 0, we have to make sure that this is contiguous, but in iOS they do not support an implementation for ISIS virtual links. So L2 must be end-to-end on a link-by-link basis. There are no exceptions for this. Now, in level 1, this is going to act like a not-so-totally stubby area in OSPF. And what I mean by this is that you're able to form adjacencies within your area. You're able to learn about those intra-area routes. You use a default route to get out towards the level 2 domain, and you're allowed to do redistribution into the level 1. So this would be the equivalent of iOS syntax if you said you had area 1 that is an NSSA, no summary. So it's a not-so-stubby area, but it is also totally stubby at the same time, which means it's filtering out inter-area routes as well as externals. So same type of behavior here for ISIS level 1, but we don't call it a stub area. We simply call it L1 or level 1. And as I mentioned, between the areas, we use the level 1, level 2 router to summarize the information from level 1 out to level 2. Now, in the reverse direction, though, since L1 behaves like a not-so-totally stubby area, we're not redistributing, we're not leaking routes from the level 2 domain into the level 1 by default. We're simply going to be using a default route to reach any of those inter-level or external destinations that the level 2 domain knows about. So the level 1, level 2 router is essentially like the area border router, the ABR in OSPF. Now, technically, the L1, L2 router doesn't advertise a default route into level 1. What it does is to set this bit in the link state packets called the attached bit. And we'll see from the output of show ISIS database, we can tell who are the valid L1, L2 routers because they will have the attached bit set to 1. This essentially means that we can use them as a default destination as long as they are the lowest cost level 1, level 2 router based on our shortest path tree. So we'll see the logic of the inter-area routing in OSPF is pretty much exactly the same as the inter-level routing in ISIS, that we solve the shortest path tree to all of the exit points out of the area, which are the level 1, level 2 routers, and then from there on, they know the shortest path tree to all of the devices within level 2, similar to how an ABR knows the shortest path tree to the devices in area 0, and then we continue on from there. So in terms of scaling ISIS, this is one of the most basic features built into it, just like OSPF areas, that we're cutting down on not only the network layer reachability information, the number of routes, but we're also cutting down on the topology information, specifically the size of the shortest path tree, by limiting where the flooding domain is for the specific link state packets. Now, one thing that's a little bit different here in ISIS versus OSPF is that in OSPF, typically an interface only belongs to one area at a time. Now, there are some exceptions to that where you can run multi-area adjacencies, but 99% of the time that's not the case in OSPF. You either say this link is area 0, this link is area 1, and they're typically mutually exclusive. But in the case of ISIS, you can establish both level 1 adjacencies and level 2 adjacencies at the same time. And this is actually the default behavior of the process, that the link level establishes both L1 and L2, which means that if you don't modify this, you essentially double the overhead of the shortest path tree. Because you run the SPF process once for level 2, you run the SPF process again for level 1, the results are equal if everyone's running all of the same levels, and then you throw half of the information away. You throw the level 2 information away. So in terms of basic optimizations of ISIS, this is one of the first things that you would want to do, is that you typically want to define the level either globally under the process or at the individual link level. Now, the reason specifically that you have the options for both of them, it depends on whether you are an L2 only router, an L1 only router, or whether you are a border router, a level 1, level 2 router. So if we were to think of this from our logical topology point of view, Let's assume that on the left-hand portion of the network between routers 4, 5, and 6, that we want to run this as ISIS level 1. And within the core of the network, let's say between these 6 devices, we're going to be running ISIS level 2. This means on router 1, XR1, router 2, and XR2, if they're only forming level 2 adjacencies, we would simply say in the global process, the process is L2 only. Then likewise on the left-hand portion of the network on router 6, if it is establishing only L1 adjacencies, then we would say globally under the process that it is L1 only. But router 4 and router 5, since they're establishing both level 1 and level 2 adjacencies, where essentially they are the L1, L2 router, it means that we would have to run L1 on the interface on the left, run L2 on the interface on the right, and then do redistribution between the 2 levels. Now we'll see that just like in OSPF, the redistribution between the levels or between the areas in OSPF does happen by default. So in OSPF, when you are an ABR, you automatically generate type 3 LSA in order to generate the network summary. Same is true with ISIS, that you take the level 1 routes, you automatically summarize them in terms of the topology information and advertise them into the level 2. But the reverse direction, when you go L2 into level 1, you don't leak the specific routes, you're only setting the attach bit, which is to use a default route out of the area, or more specifically out of the level. Now, in addition to the level of the adjacency, one of the other considerations we have in ISIS, just like we do in OSPF, is what is the network type. One of the differences, though, is that ISIS only supports 2 network types. It supports broadcast and point-to-point. And as you could probably guess, just like OSPF, broadcast is the default on multi-point broadcast interfaces, mainly Ethernet for our case. Where point-to-point, this is going to be on any truly point-to-point link like PPP or HDLC encapsulations, or like a point-to-point GRE tunnel, you would typically run those links as point-to-point. Now the reason that there is a difference between them is similar to what we have in OSPF, where OSPF defines the designated router, ISIS defines the designated intermediate system, or the DIS. Now, unlike OSPF though, there's not a backup for the designated intermediate system, which means that the election is dynamic. So preemption can occur for the DIS election, and it's going to be based on, just like in OSPF, a higher priority value, and then the higher identifier, which is called the subnetwork point of attachment, which is essentially the MAC address of the ISIS process. Where typically if you wanted to influence this, you would simply raise the ISIS priority at the interface level, and that's going to force that router to become the designated intermediate system. But we'll see within a service provider scope, in the vast majority of cases, you're not running shared Ethernet segments, you're running point-to-point Ethernet. This means on any of these segments in the core of the network, like between XR1 and XR2, we would want to run this as ISIS network point-to-point in order to remove the need for the designated intermediate system, which is an additional link state packet or an LSP within the database. So the same as in OSPF, where we have only 2 routers on the segment, we want to set the network type to point-to-point. This removes the network LSA, or essentially the designated router election and its advertisement. So when we look at SPF, it's simpler to run the calculation without LSA2 in OSPF or without the DIS in ISIS, because it's an additional step in the recursive lookup that we can skip. When we say that there's only 2 routers on the segment, you don't need to ask the DIS who essentially else is adjacent there. There's a question here, is there any loss of routing information when the DIS is lost and until the new DIS is elected? Typically no, because even though the routers are going through a convergence event, the old LSAs are not flushed out, so they rerun SPF, but the result of SPF is the same, so you generally should not have a loss in the data plane. It's only an issue if the old forwarding entry gets flushed out and then it takes time to write the new forwarding entry back in. And even though it's the same information, you might be withdrawing the route and then reinstalling it. It really depends on the platform how they specifically implement that, whether there is going to be a hit in the data plane when the DIS needs to be re-elected. But typically you don't need to set the DIS, you just let it calculate on its own. And then like the OSPF designated router, as long as you have connectivity at layer 2, that's all that you really care about from the DIS's perspective. Okay, so in terms of forming adjacency, there's mainly 3 of these options that we need to take into account. First and foremost is the transport. Can I send the CLNS packet out, and can the other device receive it? Now, if we're dealing with legacy networks like MBMA networks like Frame Relay or ATM, one of the typical problems with that is that since ISIS is not IP encapsulated,